itself. So let's start with a really big question. If you could peel back the layers of the universe, if it was all just a giant computer program, what would that fundamental line of code actually look like? Well, believe it or not, physicists think they found it, and it governs pretty much everything. To even get close to understanding it, we have to make a huge mental shift. You see, for the longest time, we saw the universe as this perfect clockwork machine, like a giant game of billiards. If you knew where a ball was and how fast it was going, you knew its entire future. Simple. But then, we stumbled into the quantum world. And down there, things get weird. Particles aren't just little billiard balls anymore. They're also these strange waves of possibility. Certainty goes right out the window and gets replaced by probability. So, these laws we trusted for centuries started to show some really deep cracks. You see, the promise of classical physics, the world of Newton, was absolute. It was this deterministic dream. Just give me the position and the momentum of a particle, and I can tell you its exact future with 100% certainty. For a while there, it really seemed like we had it all figured out. But this clean, orderly vision was about to hit a brick wall, hard. A couple of really big problems popped up in experiments that classical physics just had no answer for. It wasn't that the answers were complicated, it's that there were no answers at all. Okay, so crisis number one was the atom itself. According to the best physics we had, the amazing laws of electromagnetism, an electron zipping around a nucleus should be constantly giving off energy. And if it's losing energy, it should spiral right into the center and poof, the atom collapses in less than a second. But obviously that doesn't happen. Atoms are stable. You exist. I exist. Classical physics predicted a universe that couldn't possibly last. Whoops. And if that wasn't bad enough, the second crisis was even more bizarre. It had this amazing name, the ultraviolet catastrophe. Basically, when scientists used their classical laws to calculate the energy coming off a hot object, like a glowing piece of metal, the math just completely fell apart. It predicted that any hot object should be blasting out an infinite amount of energy. I mean, just look at the difference. The real-world experiments showed the energy was totally finite. It peaked and then dropped off. But the classical prediction? It just shoots off the chart, straight to infinity. The theory wasn't just a little wrong. It was catastrophically, absurdly wrong. The foundations of physics were broken.
So the first light in all this darkness came from a German physicist, Max Planck. And he proposed an idea that was so out there he wasn't even sure he believed it himself.
Planck kind of reluctantly said, look, what if energy isn't like a smooth, continuous flow of water? What if it only comes in these tiny individual packets? He called them quanta. Honestly, he saw it as a desperate mathematical trick just to make the equations work. And you know what? This simple, crazy idea was incredibly powerful. His little formula, E equals h nu, worked perfectly. It completely solved the ultraviolet catastrophe. By saying a wave's energy had to come in steps tied to its frequency, that infinite energy problem just disappeared. But it was Albert Einstein who looked at Planck's mathematical trick and said, no, this isn't a trick, this is reality. In 1905, he made a huge leap and proposed that light itself isn't just a wave. It's literally made of these energy packets. We now call them photons. Suddenly, light was both a wave and a particle. And this right here, set the stage for one of the most mind-bending ideas in all of science. If a wave, like light, could pretend to be a particle, could the opposite also be true? That was the incredible question asked by a young French aristocrat, Louis de Broglie, for his PhD thesis of all things. He just thought, hey, nature loves symmetry, so if light waves can act like particles, then maybe particles like electrons can act like waves. De Broglie proposed that every single moving particle, an electron, a baseball, you, me, has a matter wave that goes along with it. The wavelength of that wave is just Planck's constant divided by the particle's momentum. All of a sudden, every piece of matter in the universe had this secret, wavy identity.
And this wild idea, it beautifully solved that whole mystery of why atoms don't collapse. Think about an electron's wave like it's a guitar string wrapped in a circle around the nucleus. For that wave to exist, for the note to be stable, it has to connect back on itself perfectly. This only works if a whole number of its wavelengths fit exactly into the orbit. Any other path, and the wave just cancels itself out. That's why electrons can only be in specific, stable orbits. It's incredible. So let's recap. The pieces were finally on the table. We had energy coming in packets, light acting like a particle, and particles acting like waves. The final, epic challenge was to combine all of these revolutionary ideas into a single master equation.
The physicist who finally cracked the code was Erwin Schrödinger. He wasn't just fiddling around with formulas. No, he was hunting for the fundamental law of motion for this new quantum reality, the master equation that would describe exactly how these matter waves move and change through time.
To build his equation, Schrödinger was like a master chef. He took the classic recipe for energy, but then he brilliantly folded in the new quantum ingredients from Planck and de Broglie. He was translating the old language of physics into the new, wavy language of the quantum world.
And this is what he came up with. The Schrödinger equation. Now, don't get bogged down by the symbols, okay? Just look at the beautiful structure of it. On the left side, you have how the wave changes over time. And on the right, you have the total energy of the system acting on that wave. It's this profound, elegant statement that governs the entire story of a quantum system. It really is the source code of matter.
But what about that weird pitchfork symbol psi? What is that thing? Well, it's called the wave function, and this is key. It's not a physical wave like a ripple in a pond. It's a wave of pure possibility. It's a mathematical object that contains everything you could possibly know about a particle. And the height of that wave at any given point tells you the probability of finding the particle right there. So this leads to a really bizarre two-step picture of reality. Before we look at a particle, its wave function just evolves smoothly and predictably, spreading out like a cloud of pure potential. It's in all possible places at once. But the instant we measure it, the very second we look, that whole wave of possibilities instantly collapses into one single definite spot.
And here's the really crucial part that people often miss. Quantum mechanics isn't just total random chaos. The Schrödinger equation itself is perfectly deterministic. It tells us exactly how that cloud of possibilities will evolve over time. The randomness, the roll of the cosmic dice, only jumps into the picture at the very last moment, the moment of measurement.
And that leaves us with maybe the deepest and most profound mystery in all science. If reality is just this deterministic wave of potential, governed by this beautiful equation, then what is it about our act of looking that forces the universe to pick just one outcome out of all the infinite possibilities? What does it even mean to observe something? That right there is a question physicists are still arguing about to this very day.